Hello dear student, I am Monur Islam. Today in this video we are going to discuss an important question from CSIRNET June 2021. Okay, and this is question from part B and it is of 3 mark. Okay, and this question ID is 475. Okay, someone asked me in a in a previous video in comment section that to solve this question. Okay, so I am taking this question in this video. Okay, so what is the question? The question is that there is two statements. Okay, student 1 and student 2, and asking which student 2 and which false. Okay, so read statement 1. It said there is a matrix n belongs to M for R. Okay, n belongs to M for R means n is a focus matrix. Okay, and each entry of this is a real number. Suppose this is a matrix of the form this like A1 to A1 and ANN. Okay, so each entry is a real number. Each entry is focus matrix and each entry is a real number. Okay, and further said that this is a basis of row space. Okay, this is a basis of row space. It is a basis of row space. Okay, so since it is a basis of row space, I can say dimension of row space is 2. Okay, because this is a row space, so dimension of row space is going to be 2, and dimension of row space equal to dimension of column space equal to rank of n. Okay, so rank of n is 2. So from this we can tell that rank of n is 2, and this vector belongs to null space. Okay, so this is true or false. To verify this statement, I am going to state a result. Okay, if you know this result, this statement is if you know that result, then you can verify this statement very easily. Okay, so I am going to state this result. Okay, what is the result? Let A be an M cross matrix. A be any M cross n matrix. B M cross n matrix. Okay, right? A be M cross matrix. Then the result said that row space of A. Row space of A. This is row space of A is orthogonal. Row space of A is orthogonal to null space of A. Okay, and this is the result from AP Singh linear book. AP Singh linear book. Okay, if you learn this book, then you in the chapter 5 inner word space you get this result. Okay, and this is also has a name. Its name is called fundamental theorem of linear algebra. Means it is an important result. Okay, everyone know it like this. I thought everyone know this result. A fundamental theorem of algebra is called this result. Okay, so if you use this result, then you can verify statement 1 is false. Okay, easily. Row space of orthogonal to null space means each vector of row space, each vector each row space with null space A gives inner product 0. Okay, each vector of row space with the vector of null space of A gives inner product 0. So using this, I am going to verify this result. See, it is say that this is a basis of row space of A. Okay, so I can say row space of A I can say since this is a basis of row space of A, so these two vector span also this set span the row space of A. Okay, since it's a basis, so it is first of all linear element and it is span row space of A. Okay, so I am writing the second condition, span. Okay, so I can say from this row space of A span by this vector, the given vector is 1 minus 1. Okay, a last vector is 1 minus 1 1. Okay, since it is span to every vector every vector of this span will be, if you take any vector row space from alpha, then alpha is nothing but the linear combination of these two vectors. Okay? Linear combination of these two vectors. Okay, so in general it vector or any member of row space will be of the form like this: alpha into linear combination, two vector linear combination, 1 minus 1 minus 1 1 1, such that alpha beta belongs to scalar field, so it R. Okay, now if you choose alpha equal to 0, and beta equal to 1, okay, so you get this vector belongs to row space. Okay, So you get this, if it's alpha equal to 0 and beta equal to 1, then you get 1 minus 1 1 1. This vector belongs to row space of n, right? This vector belongs to row space of n. Okay, and it is given that 1 2 1 4 belongs to null space of n. Okay, so it is given, so 1 2 1 4, this vector given belongs to null space of n. Okay, and I've shown that this vector belongs to row space of n. Okay, now we know this is all about in Rn. Okay, in R4, this all are going to in R4 because there are 4 component vector. Okay, so all are going to in R4. So we know that in Rn, inner product is nothing but dot product. Okay, in Rn inner product of any two vector uv is nothing but dot product u dot v. Okay, so if it is R4, then inner product of any two vector uv is nothing but dot product. Okay, so for this vector, if you find the inner product, this 1 2 1 4 and 1 minus 1 1 1, this one is dot product. Okay, dot product means components of product. 1 dot 1 and 2 dot minus 1 and 1 dot 1, then 4 dot 1. Okay, so this gives 1 minus 2 plus 1 plus 4, so this gives 4. So see, this is about non-zero. Okay, this two vector inner product is non-zero, so it is not possible because we know the result, as I previously stated, that for any matrix, if n is a matrix, since n is any four-post matrix, then using the result fundamental theorem linear algebra, we always have row space of n is orthogonal to null space of n. Okay, means every vector of row space will be orthogonal to null space of n. Means every vector of row space, if suppose u with the vector of row space and v with the vector of null space, okay, then these two vector inner product must be 0. Okay, and inner product means dot product u dot v, so these two vector inner product must be 0 using the fundamental theorem of linear algebra. Okay, but these two vector is a vector of null space, this is a vector of row space, and these two inner product will be non-zero. So is it possible? It is never possible. It contradicting the fundamental theorem of linear algebra. It contradicting fundamental theorem of linear algebra. Okay, it contradicts fundamental linear algebra. So statement 1 is, I can say that statement 1 is false. So statement 1 is never possible. Such you cannot get such a matrix. Okay, such a discontinuous whole. Okay, now we observe the statement 1 is false. Since statement 1 is false, so one says statement 1 is false, one says statement 2 is not correct. It says statement 1 is true. Okay, so it's not correct. It says both statement true. Since 1 is not true, so it's correct, incorrect. So we have to verify option 1 and 3 only. Option 3 is statement 1 is false and statement 2 is true. Option 3 is false and is false. Okay, so we have to go into verify option 2. See, option 2. What it says? Statement 2. What statement 2 says? It said is that there is a matrix n for R such that this is the basis of column space. It's saying about column space. Okay, so this is the basis of column space. It is the basis of column space. Okay, so first of all it is linearly invert, and this set span column space. Okay, this set span column space. So since it is a basis, I can say that dimension of column space is 2. Okay, from this, since the basis, we know a dimension of a vector space is nothing but the number of element basis. So since the number of element 2, so dimension of column space is going to be 2. Okay, so I can say that from this dimension of column space m, you can write like this: dimension of column space of m is 2. And in previous video I have already told that dimension of column space is nothing but of nothing equal to the rank of m. Okay, because it is nothing but dimension of column rank. Okay, and we all know for any matrix m cross n, for any matrix, column rank equal to row rank equal to rank of m. So column, it is column rank and column equal rank. So for the matrix rank of is 2 given. Okay, for the matrix rank of is 2 given. Now it is also said that in the question there is also one more statement. Okay, I have mistake that part. There are some vector, I think in this question there in this part there also there one statement. Okay, I forgot to return this statement was I am telling this statement was with this statement start. Okay, with this and one more statement is attached. Okay, one more condition is attached. So what is the condition? That was condition I am writing. Okay, I forgot to write that. Sorry for that, I forgot to write it. That was this vector 1 1 1 0, this vector, and one zero one. Okay, this it says, I think it transpose. Okay, it belongs to null space. Okay. In this case there are two vectors. In statement 2 there is two vectors. Statement 1 is one vector. Okay, so these two vectors belongs to null space. It is also given in the statement 2. Okay, so tell me these two vectors are linear independent. Okay, I have observed that the rank is 2. Okay, and it also given that this vector 1 1 0 and 1 0 1. Also given that 1 1 0, sorry 1 0 and 1 0 1. Okay, this vector transpose also given null space of M. Okay, since rank is 2, so using this I can say that nullity M plus rank M equal to number of column M is 4 matrix. Okay, given that M is 4 matrix, M for R, M is 10 for R, 4 matrix, so number of column is 4. Since rank is 2, okay, so I can say that nullity M is 4 minus 2 is 2, so nullity is 2. If you observe this vector is linearly independent. Okay, this vector is linearly independent. Take it combination, you get C1 3 0. If you take it combination 1 1 0 plus beta into 1 0 1, and this alpha vector, so 0 0 will be 4 0. This is alpha plus beta equal to 0, and second vector is alpha equal to 0, and this is alpha plus beta equal to 0, and this is beta equal to 0. Okay, so you got alpha beta equal to 0. Since both scalar are 0, so this vector is linearly independent. This vector is linearly independent. Okay, also it is given that it's also the condition 1 is said that rank nullity M is 2. Okay, so this vector going to form a basis. This vector going to form a basis of null space on. Okay, since linear independent and also nullity M is 2, so this vector going to be a basis of null space on M. Okay, I am saying that this vector going to form a basis of null space on M. Okay, it may happen that null space contain more other vector than two vector, because it can happen that there also another vector can belong to this vector, but this vector is linearly dependent with this vector. If some vector belong to null space M, then other than this vector, then this vector is linearly dependent with this vector. Means the third vector, if the another more vector belongs to null space M, then the third vector will be linearly dependent with two vector. Okay, so null space dimension null space 2. Okay, otherwise other rank will be violated. If there is one more vector which is linearly independent with two vector, these two vector 1 1 0 and 1 0 1, then if it is linearly independent also, then it violates the rank theorem, because rank is 2, then nullity is more than 2, then rank nullity does not give number of column is 4. Okay, so it is not possible. So if any vector other vector belong to null space M, then this vector obviously will be linearly dependent with two vector. Means is the linear combination of these two vectors. Okay, so statement 2 is true. Okay, I am not getting any contradiction in statement 2. This is true. So in the question, student 1 is false, student 2 is true. So option 1 is correct, option 3 is incorrect. So okay, so in this question, correct option are option 1. Okay, so student 1 is incorrect, student 2 is correct. Okay, so if you any doubt, you can always ask in the comment section. Okay, and more video solution will come in upcoming videos. And if you have any doubt in a particular question, you can comment me and ask me that question. I will take this question in the next video. So thank you.